AC charging is given its name because it is AC power going to the car. While we all tend to call the wallbox or other AC brands a charger, it can be better described as a controlled safety switch, setting up a signal to the car telling the car how much electrical current it can charge with. A more technically correct name is a charging station, but it has many different names. The car will use the same signal to turn the charging station on and off. So, the charging station sends a signal to the car and waits for the car demand to switch power to the car. Then, when the battery is charged, the car will turn off the charging station and the charging station will once again be waiting for car demand. The size, as an electrical design capacity, of the charging station will determine the maximum signal to the car, and the size, as in the designed electrical capacity of the car's onboard charger, will determine the maximum charge rate in kilowatts for charging the car. It is recommended to choose a charging station that can vary the signal to the charging rate of the car so that it can be controlled. This is because the charging of an EV is such a big load on a house or a building. The signal to the car is known as the control pilot signal, often shortened to CP signal. An example of this signal is shown on the right-hand side of the diagram. So what actually determines the charging speed of an EV with AC charging? Either the electrical capacity of the charging station and the onboard charger match perfectly, or it is the smaller of the two that will restrict the charging to a lower and slower rate. Don't fall into the trap of always thinking that you need to charge fast though, because control of charge can be much more important than speed of charge. Ultimately, we want our cars charged when we want to use them, but we don't want to overload the electrical supply when charging them. Using kilowatts as a rating for any AC charging station can make it confusing. The exact same device in America uses the current rating, for example 48 amp. Normally, things that generate and use power are rated in watts or kilowatts, and anything that carries or switches electricity is rated in amps. For example, a light switch will be rated in amps, and a lamp would be rated in watts. Using this logic, the American rating for an AC charging station makes more sense. It really doesn't matter what it is called, as long as we understand what it is doing. Otherwise, it is easy to have mismatching charging infrastructure that will not give you the results you require. This slide is an overview of the 4 common onboard charger sizes found in an EV. There are some small variations of 1 kilowatts either side of what's stated there, but what this shows is the electrical supply to enable the various onboard chargers to run at their maximum capacity. It is useful to remember that this is the most current that they will be able to use. However, they will work down to 6 amps at a minimum. The green squares represent the onboard chargers, and the coloured circles the charging stations and electrical supply. All onboard chargers will work from that minimum of 6 amps up to the maximum designed limit. We have now narrowed this down to the 2 different onboard chargers that about 99% of all EVs sold here in New Zealand will have. Time for a great rule of thumb. 1 amp for 1 hour will add about 1 kilometre of New Zealand highway range. This covers a wide variety of EV and allows for plenty of hills plus the use of aircon, etc. 1 amp for 1 hour, adding 1 kilometre, is the equivalent of using around 23 kilowatt hours of energy per 100 kilometres of driving. This data is shown on most EV, and around town in a small EV you will be much closer to 12 kilowatt hours per 100 kilometres of driving. But we would rather have a rule of thumb that errs on the side of caution. A larger EV driving at highway speeds with a heater on can easily use around 23 kilowatt hours per 100 kilometres of travel, and of course you will use a lot more energy if you're towing. The next 3 slides show different configurations of charging stations and onboard chargers. What we see in this slide are a pair of charging stations, often referred to as 22 kilowatt. They are charging stations rated to switch 32 amp 3-phase electrical supply to an EV. The round circles represent the 3 wires that are capable of carrying 32 amps. There will also be a combination of smaller circles which represent wires and electrical infrastructure capable of carrying 16 amps of electrical current. A circle that is solid in colour represents a supply that is carrying current. and a circle that it does not have colour on the inside represents potential, a wire that could carry the current but is not at that time. The first car to come in has a single-phase 7.4 kilowatt onboard charger, which will take 32 amps from one phase, enabling the car to charge at 7.4 kilowatt, but only utilise one of the three phases that are wired to the charging station, approximately 33% of its installed capacity. The next car to come in has an 11 kilowatt onboard charger. This will take 16 amps from all three phases. The half-filled circles in the charging station represents wire that are flowing half the capacity that they could supply. The three-phase 16 amps that an 11 kilowatt onboard charger can accept allows for an 11 kilowatt charge speed, which is utilizing 50% of the installed capacity of the charging station. In this example, we have a three-phase 16 amp charging stations, mostly referred to as 11 kilowatt. The first car coming in has an 11 kilowatt onboard charger. This is perfectly matched to the three-phase 16 amp charging station and will allow the car to charge at 11 kilowatt, utilizing 100% of the installed capacity. However, things are not so good when charging a car with a 7.4 kilowatt onboard charger, because this can only take current from one phase, and a 16 amp three-phase charging station only allows for 16 amps per phase, which results in a 3.7 kilowatt charge rate. This is only utilizing 33% of the installed capacity of the charging station, and the car can only charge at half its maximum rate. Now we have a 32 amp single phase charging stations. The electrical supply and protections to these are much smaller and more cost effective. So let's see how the charging works on these. The first car coming in has a 7.4 kilowatt onboard charger, which is matched perfectly with the 32 amps that the charging station can supply, enabling a 7.4 kilowatt charging rate and utilizing 100% of the installed capacity. The second car coming in has an 11 kilowatt onboard charger. It is useful that the 11 kilowatt onboard chargers can also make full use of a 32 amp single phase supply. The flexibility of this type of onboard charger is very useful for when planning efficient charging infrastructure. Remember that relative to filling a car with petrol, replacing energy in an EV will always be slow. Just like our phones, start the day on full charge. In most cases, control of the charging rate is more important than the ultimate fastest rate. If you start the day with 300 plus kilometers of range, there are not too many cases where charging at 48 kilometers per hour is more useful than charging at 32 kilometers per hour, especially when control and flexibility is compromised. Let's take a look at how we can control the charging rate with the various options. This graph will show the working range for the various onboard chargers. When we rate an onboard charger in kilowatts, this is the maximum, like we said previous slides. It can also operate at a lower power rating, just like a 2000 watt heater can also operate at 1000 watts at a lower setting. The amount of current that the onboard charger will use is set with a signal from the charging station or the portable charger. Here, a 3.7 kilowatt onboard charger will work between 6 and 16 amps, enabling between 1.4 and 3.7 kilowatts charging. A 7.4 kilowatt onboard charger will work between 6 and 32 amps, enabling between 1.4 and 7.4 kilowatts of charging. An 11 kilowatt onboard charger will work between 6 and 16 amps, three-phase. This means that the charge power is between 4.2 kilowatts and 11 kilowatts. If we consider our rule of thumb, with 1 amp for 1 hour adding 1 kilometre. In this case we have 3 lots of 16 amp, so charging at full speed will add the 48 kilometres of New Zealand highway range. While the top end charge speed is slightly better, the lower end control is not good. As a comparison, imagine trying to drive a car where the accelerator didn't do anything to make the car move forward until it was almost halfway down, and then when it did start to move, you had too much power. You'd be driving around at normal speeds with the accelerator either on or off, and it wouldn't be smooth at all. Nice control is smooth and doesn't have to turn on and off a lot. That looks after controls and protections and switchgear. As more cars need charging, control becomes important so that the charging process can work within the constraints of the electrical supply, which ultimately ends up in translating to cheaper energy prices. The same is true when wanting to charge the car using spare renewable energy at home. Having a control at slower charge speeds is actually an advantage. We also need to remember that most New Zealand families have more than one car, so there will be a requirement to charge more than one car. Some will choose to do this by sharing the one charging station, but a lot will want the convenience of just plugging in and letting the smarts sort the rest. We have seen many homes install 2 charging stations already, with a few installing 3. An interesting side note is the types of onboard chargers and charging stations that can be used in America. They use a Type 1 charging connector, so there is no possibility of 3-phase. But the extra current, 48 amps, allows for the higher current charging rate without compromising the lower end control. The reason we are introducing this now is because if you do want to future-proof and consider installing single-phase wiring that is capable of carrying the 48 amps. No charging station or onboard chargers can use this in New Zealand at the moment, but if someone were to private import a Ford Lightning EV or one of the equivalent other American EV pickup trucks, then they can install a 48 amp charging station to enable these vehicles to charge at the full rate. Note that because these vehicles are single phase, if you plug them into a 3-phase 32 amp supply, otherwise called 22 kilowatt charging station, they will only be able to take current from the one phase and charge at a rate of 7.4 kilowatts. The Type 2 standard was originally designed to allow for 63 amps per phase. So while there are no cars here at the moment with a Type 2 charge port that will take more than 32 amps, it is possible that onboard chargers in the future will be able to charge at 11 kilowatts using either 16 amps 3-phase or 48 amps single phase. For this reason, installing wiring rated at 48 amps can be considered future-proofing. While most situations do not require this charge rate, it may be useful to be able to enable it for short periods or circumstances in the future. Now let's see how the charge rate translates to range adding capacity over an 8-hour charge session. Most cars are parked for extended periods, so 8 hours is a conservative assumption for how long a car will be on charge. At 1.4 kilowatt, the lowest charge rate for most onboard chargers, you can easily add 50 kilometers of range. At 2.8 kilowatt, you will add 100 kilometers of range. 5.7 kilowatt adds 200 kilometers of range. 7.4 kilowatt is the maximum for 32 amp single phase charging, what we recommend for most infrastructure, and this will add 256 kilometers of range over an 8-hour charge session. 11 kilowatt will add 384 kilometers of New Zealand highway range, assuming an isolated case where you only charging one car and have plenty of capacity. But how many situations are there when 256 kilometers of range per 8-hour charge session is not enough and you'd actually need the extra 16 kilometers per hour? As we will see in the next slide, the real world performance from a 3-phase charging setup can be quite a bit different to theory. If you've got a single phase supply to your home, there's no option or any requirement other than to connect it to the charging station as single phase. You can utilize a sensor to monitor the total power that the house is using, and in combination with this and power sharing, there's plenty of potential EV charging capacity with a single phase supply. So don't go and spend money upgrading your supply just for EV charging. But even if you do have a 3-phase supply to your home, it's still highly recommended to install the charging stations as single phase. And let's look why. An electrician will always try to install electrical devices so that the 3 phases are balanced as possible. However, in practice, there will always be out of balance to varying degrees. Here's an example of a 3-phase load. If the EV charging is installed as 3-phase, then it can only work by using the same amount of current on each phase. This means that it can only work using the spare capacity equal to that on the most loaded phase, represented here by the brown boxes. Add a second 3-phase charging station and a 3-phase car, and the problem only gets worse with a lot of potential charging capacity that just can't be used. What we see is all that spare capacity on the white phase and the blue phase. If the first car is single phase, then there won't be much power to charge the 3-phase car either. If both charging stations are installed as single phase, then they can each work with the spare capacity on each phase. What you do is install the different charging stations on the different phases. Some larger homes may even want to add a third charging station, which would go on the third phase. Once there is a charging station on each phase, you can then start to add multiple charging stations on the other phases. And they will power share and monitor the spare capacity so that you will get the maximum range adding capacity from an installation. Clearly, we're now moving away from what a house might have and looking at what a small commercial site may require, but the reasoning stays the same. This here shows the power sharing that would happen on each of the phases at either a home using 1, 2, or 3, or a larger commercial site. The key thing is that each phase would have its own power sharing network. The system would know how much power is available and automatically control the charging to give you the maximum range adding capacity without overloading any of the electrical supply. As you can see here, there was enough for 7.4 kilowatts on both cars. Third car comes in, they ramp down. Fourth car comes in, they ramp down again. And then a car finishes charging or leaves, it redistributes that power. This has been an introduction to single-phase and three-phase charging. We have a video that adds to this with how to plan to have charging in larger installations and how to calculate the charging power and electrical current required. Please contact us here at Transnet eMobility, where we can help you with your EV charging requirements.